Okay, well, I think we'll make a start. We've got plenty material to go through, and I'm sure you want to get through as much of it as you possibly can. I'll just say a quick sort of hello, introduce the session, and I'm going to be handing over to Tom, who's running the workshop. So my name is Peter Crocker, one of the co-founders of the company, Oxford Semantics, Oxford Semantic Technologies, and yeah, pleasure to have you this afternoon to come and have a look at what is reasoning, get experience with our product, RDFox, and hopefully come away with some experience of how you could use this with a very hands-on session. Tom's going to be running us through. If you can't follow along on your own machine, you're still going to get plenty out of this because Tom will be showing you, I think, everything you would otherwise be doing. So plenty of opportunity to get stuck in. We've got a decent number here, but I think there's plenty of opportunity for questions. So if you do get stuck at any point, there are going to be a few of us sort of lurking around. Chen Si, put your hand up. That'd be great. So Chen Si's one of the team as well. And yeah, I think with that, Tom, over to you.
Cool. Thank you. Yeah. Welcome, everyone, to the ultimate guide to semantic reasoning. We're going to be covering a few things today. The focus is going to be like almost entirely reasoning based, but then we're going to touch a little bit at the end on how this kind of relates to RAG, which is sort of one of the buzzwords at the minute, one of the hot topics, and has been spoken about loads throughout the conference already, and we're like halfway through day one. So yeah, as Peter said, questions are not just welcome, but really, really encouraged. The point of this workshop, at least, is sort of to teach you and to bring you up to speed with what or what reasoning has to offer. And so, if I'm going through something too quickly, or if I've not like explained something well enough, or anything, or even you just want to go down a diversion that I'm not immediately going down. This is an opportunity for us to have that conversation. So just like raise your hand or shout out or interrupt me or whatever, and we can go from there. There are a couple people still filtering in, so if you do want to follow along, scan the QR code on your desk, and you can like download the exercises and the data and all that stuff. So can I just get a show of hands? Who is following along? Like 1, 2, 3. Sort of. Okay, cool. That's fine. There might be a couple of like setup steps. So for those of you, well, not might be, there are a couple of setup steps. So for those of you who aren't following along, we have a demo that you can play with. But for those of you who are, if you get stuck at any point, and I expect that you will, because in a room this big, there's always a few. We have Chen Si and Peter and myself like dotted around so we can help. So again, please just raise your hand as early as you can, and we can get it sorted quickly. But as I said, all of this is about reasoning. So I want to share with you some motivation as to why we're even giving this session. What can reasoning do for you? Well, on the left here, we have a query that's just written without any reasoning, without any rules in the system, and it's pretty long, pretty sort of complicated. I certainly couldn't see what this like does at a glance, but on the right, I'm going to do that a few times. On the right is functionally the same query, so it gives you the same results, but it's much shorter, and this is after we've added some rules. So straight away, you can see that it's going to be quicker to write. Easier to share, easier to debug, that sort of thing. But also, if you'll see in the bottom right-hand corner here, this is the time that this query takes to execute. And the one on the right is about 4 times faster. So even with what is a relatively simple query in a real practical setting, you're getting a speed up of 4x. So imagine this scaled to a production system where you can really get like vastly quicker queries out. This is not all that reasoning can do. There's a lot that goes beyond queries, but this is a fantastic entry point, and it's a great sort of motivator for people to get going with it. We've had a few people come in. That's awesome. There's a QR code on your desk if you do want to follow along and like do exercises and that sort of thing. So scan that, we'll send you a package, download and kind of go as we go if that's all right. But yeah, we'll get you going. Everything that we're going to cover today revolves around the Sport Formula 1 and one of our old demos, which lets you ask the question, who is the greatest Formula 1 driver of all time? And that's actually a bit of a subjective question because there's loads that goes into a good driver. They have different cars, so just because you're winning a race doesn't mean you're a good driver, it might just mean you've got a fast car. So our demo here lets you sort of play around with all of those pieces and sort of figure out what you think would be would determine the best driver in your sort of situation. So it emulates a business scenario where there's lots of parameters and it gives you the control to make your own decisions. It's live at f1.rdfox.tech, so particularly during the setup stage, if anybody's sort of got a minute of like downtime or anything like that whilst we set up, check it out, it's pretty cool. And the reason that we're showing you this is because all of the queries, all of the rules, all of the axioms that we're going to write are all part of this demo. So they really are being used by us for a sort of real system. It's not just a like academic exercise. The hope is that this stuff, while it's not by any means a comprehensive overview, it is going to be enough to give you the foundations to kind of go away and build something real, or at least start asking the right questions or looking in the right places for your production systems. As I keep saying, this is like a follow-along workshop, so if you do want to follow along, scan the QR code. There are instructions within. I'm going to go through them now. I might leave some people behind, but we do have some people in the room, Chenzi and Peter, who are going to like help out if anybody does get stuck. Please raise your hand as early as you can because we've never done a workshop where like everyone's got through smoothly, so it's much easier for us if you kind of get in early, we help out, and we go from there. But yeah, that's fine. The second thing, I'm going to be going through all of this in VS Code. You are going to need some kind of like text editor or ideally an IDE. Obviously other IDEs are available. Use them at your own peril. I'm not going to go through the setup for all of them because there's like 1,000. So if you're really confident, please use what you want. But if you're not, please use VS Code. And if you do, if you run into any problems, we will come around and fix it for you. Okay, so that's the sort of intro done. What are our objectives? First is to cover the real basics of what is reasoning. Then we're going to get you set up with RAFox. This hopefully will give you a minute to download that package if you're wanting to do that. And then we're going to run through some queries. Then we're going to actually move on to the reasoning itself. So all of that just allows you to kind of access this reasoning part, where we're going to run through a handful of OWL axioms and then a bunch of Datalog rules. So many of you will be familiar with OWL. It's the sort of, it is the standard. Less of you will be familiar with Datalog, but it's a much more expressive language that allows you to do things that go beyond queries like I've mentioned before. So that's where we can do things like aggregates, negation, filters. We can even do stuff like recursion that goes way beyond what is even remotely possible with queries. It's a much nicer language to work with. So the focus really is going to be on that towards the end at least. All right, I'm going to stop there. Does anybody have any questions at this point about anything at all? Because, yeah, we love questions here. Okay, cool. So, I've just realised I might have some people online who need a link to the download page. Right. Apologies, folks online. If you want to follow along, you can do so here. Okie dokie. So, what is semantic reasoning? Well, it's been mentioned quite a lot, as I've said, but often in sort of vague terms. But really what it does is it helps you enrich your data store. It takes the context of your data and expert knowledge that is encoded into rules, and it adds to your data store. So you end up adding new triples to what you have already. This really allows you to ask and answer more complex questions, and that's really where it empowers RAG, because it takes you beyond the sort of the traditional RAG approach that just allows you to answer or ask very simple, basic questions, and empowers you to do much, much more. As we've already said, it drastically improves performance and also allows you to do things that go beyond the functionality of queries alone. That second piece we're not really going to talk about today, so if anybody does want to chat about how you can use this to go beyond queries, either catch us at the booth or stick around afterwards and we can have a chat. But the main thing we're going to look at is performance enhancements during this session. There's a final piece though that is incremental reasoning, which means all of this, all of the addition of triples, addition of data, happens automatically and in real time as you add new data that is impacted by these rules. So again, we'll kind of demonstrate that later, and it might not mean much right now, but later when it becomes super easy, hopefully you'll see the power in that. And again, to add a bit more context, or an example of a rule would be what you can see on the left here. We have our raw data about our company, OST, and our 5 founders. And a rule that we've written is count the number of founders. So all RAFox will do is literally count the number of founders and add the triple OST has number of founders 5. So now instead of doing that count every time we query, we can directly access this piece of information, which obviously is much, much faster than doing the count. And I've mentioned it a few times, but we're going to be working with RAFox, which is a knowledge graph and reasoning engine. Hopefully most of you guys know what a knowledge graph is, and by the end of this you should know what a reasoning engine is too. We have this incremental reasoning piece, which is pretty special, and again we'll get to that slightly later. It's incredibly fast and scalable, so we go from everything on device, on edge device. We actually have an instance running on a Raspberry Pi or an Arduino or something on our booth. So if you're interested in that, come check it out. But we also go all the way up to like huge AWS instances and can import Wikidata in like a couple of hours or something like that. So yeah, huge scalability, and all of this comes from our Oxford pedigree. So lots and lots of work was done for the past several decades by 3 of our professors who ended up spinning out the company with Peter and our other founder, Adam. Okay, so now I'm going to get on to the setup of RAFox for those who are going to follow along. For those who aren't following along, now would be a good time to check out the demo. But does anybody have any questions? Cool. Right, so step 1, download the package. Hopefully everyone's done that. If not, it is not too late. You still have time, but I'm going to obviously move on. Is anybody having any trouble with that, by the way? It might have taken a minute. We have to go through them like manually. No, all good? Cool. So once you've got the package, downloaded it, I'm going to want you to open it in VS Code. So pretty simple. Just go to VS Code, hit File, and Open Folder. And you want to find the folder that we've just given you, that you've downloaded. The kind of really important parts are that you have one layer of CDL24 at the top here, or in the top there. Particularly if you're on Windows, something that happens all the time is when you unzip a folder, it puts it in a folder of its own name. I don't know why, it's Windows. But if you open the sort of outer one, that will like mess the commands up. So we'll run into some problems there. So make sure you're doing that. If you do see 2 layers, just do the same thing again, file, open folder, and that in a folder. Once you've done that, you're going to want to open a terminal, which again, pretty simple. Just go to terminal, new terminal, and then, depending on what file system you're using, you're going to want to run one of these 4 commands. I'm on Mac ARM, so I'm going to use the top one. You may not be on Mac ARM, don't use the top one. But if you're copy and pasting this, be careful that it doesn't introduce spaces, that it doesn't get rid of like any of the slashes or the underscores or something like that. Again, I'm not sure why that happens often on Windows, but just be a bit careful when you do. But by doing that, we are going to start RDFox, and then we're kind of good to go. So, I've got this message here that the REST endpoint was successfully started, and that's a pretty good telltale sign that I've done the right thing. So if you're seeing that message, you've probably done the right thing. If you're not, yeah.
Is RDFox free to use for a certain time on your own laptop, etc.?
Yes. So
How does it work?
you can get a 30-day free trial. Actually, by like participating here, you've already got a 30-day free trial. So yeah, you're welcome. But after that, I think you can get up to 2 more free trials, and then we need to go into some additional thing. We normally give, or not normally, we can give up to 3 free trials because of our licensing with the university. But yeah, then it's a paid model.
Can you show the command again?
Yep. I should say as well, this deck is in the folder that I gave you, or that you downloaded. So for all of these instructions, they are in the slides from slide 10, I think, and these are on slide 12. If any of these, if you're running this and you're getting problems, there are common fixes on slide 14. Check those out. But also, please do raise your hand if you're encountering any issues, because yeah, we always encounter issues. Yeah?
Can you go back to the command?
Of course.
It's quite a long command.
It is.
Brilliant, thank you.
So yeah, if you want to copy and paste this, it's in the deck, which is in that folder. So, and you should see on slide 13, you should see the sort of output, which if you're doing it all right, should say something like the REST endpoint was successfully started. If it says something else, that's a problem.
In the background?
Yep. Anybody running into issues here?
Somebody online.
Oh yeah.
There's an Andrew online who's asked, you can't process an Andrew without knowing his surname.
Cool. It sounds like Peter's got you sorted, Andrew. So hopefully you should hear from him soon. All right. I really don't believe that there are no problems. This has never happened. So.
Yeah.
Yeah.
Could not be loaded.
Awesome. Chenzi, could you help out? Thank you. It's never just one either. There's no way. I don't believe it. Is anybody else sitting there just like confused and like not really sure what's happening? No?
Yeah.
All right. On your head be it. So let's have a look at what we've just done. We've just started RDFox in sandbox mode, which is a sort of playground. We've used a start script, which has done a few things. First, it's created a data store. We've called it F1. You can obviously, in your own time, call it whatever you want. We've activated it so that we can work with it in the terminal. We've imported some prefixes, set the output to out, and started the endpoint so we can access it via our nice UI. Or if you wanted to use any like APIs, you'd have to go through this first. But again, this is important to know should you wish to use this in your own time, because you will have to run these commands or something similar. Okay, so once you've done that, we're going to open the UI and move away from the terminal for a while. We're going to have to go to localhost :12110/console. And you should be welcomed with a screen like this, and simply select the data store F1. Sorry? 12110. This guy here. Sorry, is that big enough for everyone? Bit small at the back. I don't know if that's going to do much for my bar, but that might help a little bit. Okie dokie, so we've opened up the console, we've selected the data store F1. Now it's time to import some data. And again, this is in the folder that we gave you before. There's a folder within that folder called data, and a file within that folder called up to 2020. You're going to want to first click add content in the top right hand corner of the console, then just drag and drop the data up to 2020, which is here, into this window. Again, there are a few files here. The only one we want is up to 2020. The reason for that will become clear as we do this like big reveal right at the end. But for now, just up to 2020. You'll see a little sort of preview there, and just click add content. And in about a second, it's going to add 4.5 million facts. So fairly speedy. We just click OK, and we're good to go. So
Does it support importing trig?
yeah. Yep. Yeah. Cool. Is anybody not been able to do this? Because I am going through this quite quickly. I would normally spend a lot more time on this, but we're quite pushed for time today. Nice. All right. Still, Chenzi's floating around, so if anybody is like not brave enough to tell me, but is to tell her, she'll help. So let's have a quick look at what you've just imported. This is historical race data from the Sport F1. It has everything about drivers, races, constructors, everything. It's awesome. The people at Ergas have done a lot of work to like put it in this shape, and we have just nicked it. You can explore a little slice of this, which I would suggest, by going to the next slide and clicking on this link. And it'll take you to our Graph Explorer. And it may look a little bit different to this. Every time you reload the screen, the graph is laid out in a different way, but the data will be the same. And this is not like all of the data or anything like that. It's just a comprehensive slice. So, for example, if we dive in on a driver, Lewis Hamilton, we can see that he belongs to the class driver. Classes are in green, instances are in purple, and that he has a bunch of these properties. So if, for example, later on, you want to access the forename of a driver, you'll need to know that the way that we do this is with the property driver underscore forename. Hopefully that's not too difficult, and yeah, just if you want, keep these tabs open and like refer back to them as and when, because the exercises later will be sort of fill in the gap type exercises, and it will be helpful, or we often find it's helpful to sort of refer back and like pinch parts where you need them. Awesome. I've just managed to catch up to where I'm supposed to be at this point. So, thank you. We started a little bit late, so I was a bit worried about time, but I think we're back to it. So I'm going to take a minute. Do we have any questions at this point? Because I've really thrown a lot at you very, very quickly. Yeah?
A technical question.
Yeah, please.
You said a lot of stuff, but you didn't say all. We're not gonna.
We are going to touch OWL. We're going to look at 4 OWL axioms. They're pretty basic, and the reason for that is we're going to focus on Datalog, and everything you can do in OWL you can do in Datalog, but then you can also do loads more stuff, and at least I personally find Datalog much easier to work with. The syntax is intentionally close to Sparkle. So if you can write Sparkle queries, you should be able to write, or at least very quickly pick up Datalog. Whereas OWL, are you familiar with OWL? Yeah. So the syntax can be like challenging sometimes, and a lot of the time you end up going through a tool like Protégé or others that are also a challenge to work with. So yeah, we are going to touch on that because it is the standard. People do like it because it is the standard. But yeah, we'll be focusing on Datalog. Right. So before we jump into reasoning at all, we're going to cover 3 Sparkle queries. They're going to get much harder very quickly, and you will hopefully see what I mean by that, because the first one is just the basic select query, the most fundamental query that you can write. Some of you, anyone who has written Sparkle will recognize this because they write it all the time. But anyone who hasn't, there are a few key components of this that we need to cover to make sure you kind of are familiar with all of this going forward. This is where the exercises start. So if anyone is following along, from slide 20, there's going to be a link in the bottom right corner to open it in the console. You can go ahead and click that, and it will open it in the console. That's fine. I don't know why I'm whispering. There's a QR code there. Give that a scan. Someone will send you a package. The instructions start on slide 10, so hopefully you should be able to follow along. But Chenzi is also available to help you through that if you need it. So just stick your hand up. Cool. So where were we? There's a few key parts to this, and we're going to go through them one by one. But they're fairly simple. The first is the select keyword at the very top left. This just describes what type of query we're writing and what RDFox needs to do with the information that you're providing it. Select is just a find and return query. There are many other types available, but select is the only one that we're going to be covering because the others are a bit more advanced, to be honest. But again, if you want to talk about those, stick around afterwards, and we definitely can. Underneath it is the where clause, and this is where we describe the pattern in the graph that we're looking for. And in this case, we're trying to find all of our data. So the function of this query as a whole is to return our entire data set. So not perhaps the most functional, but definitely very, very important. The pattern we're describing here is a triple pattern. So within this where clause, you can make the graph pattern as complex as you like, but here it's just a pattern of a triple because all of our data is in triples, and we want to find and match all of our data. In the subject, predicate, and object position of this triple, we've used 3 variables given by the question mark and then any characters you want afterwards. We've called it SP and O, kind of by convention, but because it's convenient for us. And this is just a variable in every position of the triple, which of course would match every triple that we have. The final piece of the puzzle is all the stuff next to select, and these are the output variables. So of the pattern that we describe within the where clause, a lot of the time this is going to be like huge and very complicated, and it's going to involve pieces that actually we're not interested in seeing. And so on the output, we just put the variables that we actually want to return in the results table. In this case, though, we do want all of it because we want all of our data. So we have S, P, and O on the output. If you go ahead and click Run, you will see in the results all of your data. So again, probably not super helpful as a visual result set, but it is there for when you need to sort of export everything or whatever. Query number 2 is about counting our drivers' races. So we're taking a pretty big leap here. There's a bunch of new stuff that we're going to throw at you all at once. But again, I'll sort of go through it bit by bit to try and keep everybody up to speed. There are now 2 links. One says open in console, one says answer. You'll notice that there are some gaps, these 3 underline. This will give you an error. Anyone who's following along, please click open in console, and you will get one that is not filled in. And I would really appreciate you trying to fill in these gaps yourself. I'm going to go through it on the fly, so I'm afraid we don't have time to sort of sit around and mull with it. But if you do get stuck, click on the answer, and it will have a complete one for you. I'm going to cheat a little bit and go straight to the answer so that we can all see it together. Because again, there are a few key parts. You'll notice that the where clause is getting a little bit more complicated. We're now using specific predicates. So result driver and result race are specific predicates in our data. And we are looking for, as I said, the drivers and the number of races that they've raced in. So for this, we need to find the drivers, associate them with a race, and in our data, in the sort of snippet that you might have been exploring earlier, we have to do this via a result. So a result is associated with a driver and a race, and now we have to link the 2. So the output also looks a little bit different here, because we are returning driver, as you might expect, but we're also doing this count, counting the instances of the variable race and saving that count as race count. So combined, we're returning the drivers and a count of the race. Pretty simple. The final couple of pieces are at the bottom here. The first is group by driver. We need to tell RDFox how to group these counts, because we don't just want a count of all the races that have ever been raced. We need to give it the context that a driver is the thing we want to group by, because it doesn't know what a driver is, doesn't know what a race is. So we have to say group the count by race by drivers, and then we will get the total number of races per driver. Finally, we're going to order by descending race count, just to give us a bit of a more usable list. So if we click run on that, we have drivers on the left and their race count on the right. Was anyone ever able to follow along with that? Yeah? Awesome. Cool. Anyone else? It was a pretty rapid. Yeah? Awesome. Great. Anybody not able to follow along with that? 1 and 2 but couldn't? Sorry. Somebody still waiting on their email. That's a bit of a blocker, I'm not going to lie. Sorry.
Go 5,000 firewalls with my company person.
Yeah, sorry. Okie dokie. So, the final query we're going to look at today is around calculating a win percentage. So hopefully you can see why we've admittedly rapidly built this up over the last couple of queries. We're now going to compute something that is actually valuable to us. The win percentage for each of our drivers. And that, of course, involves counting the total number of races, but also the total number of wins. But there are a couple of complications here. So let's dive through these one by one. Okie dokie, so we're looking for drivers and their win percentage. So first and foremost, we need some information about the drivers, their forename and surname, so we can get a list of names. And then we're going to go into actually performing these counts. But to help us do this, we need to use an inner select query. So you'll notice that we have another select query here. We've opened up another set of curly brackets and just written the same count select that we did previously. So hopefully nothing too new there, but the interesting thing is that it is within another query. And then we've performed a second count query that looks almost the same, except now we've got that the result position order must be 1. So it must be a win. And we're counting these number of races and saving this as a new variable, race win. The problem here, though, is that this graph pattern, it assumes that the driver has won a race, which sounds about right, but what if a driver hasn't won a race? Then they will be excluded from this result, and the larger query will not return them as a driver at all, which is not what we want, because a win percentage of 0 is pretty important, particularly if you're tracking this over time and seeing how that changes. So you'll notice we've stuck an optional keyword in front of the second inner select, and this just tells RAFox that this next part of the query is optional. What it will do is, if this graph pattern is matched, it will perform the inner select as normal. If it is not, it will just leave any variables that would have been defined, i.e. race wins, as undefined. It won't throw a problem, it'll just keep on going. That causes us a problem though, because we now need to sort something out and do something about our undefined variable. And so we use this bind to bind our undefined variables. To help us, we use the coalesce function, and what that does is it takes an input variable. If it has a defined value, it just returns that value. If it doesn't, it returns the second argument, which in this case we put as 0 because we know if this race wins wasn't defined, it was because they didn't have a win, which means their race wins should be 0, and so we bind race wins final as the output of this coalesce. The last thing we have to do is actually perform our calculation of the percentage, which is pretty simple now, just race wins final divided by race count, save it as percentage. So we're returning a whole bunch of stuff on the output, but just we're expecting a list of names, their race count, race wins, and the percentage. So if we go down, rerun this, we can see that we have Lee Wallard at the top with a 50% race wins. Pretty impressive, but he's only got 2 total race counts. And then folks like Hamilton, a little bit further down, but 266 race counts and a 35% win rate, which if there are any F1 fans in the room, you'll know that's not true anymore. If you'll, remember back to the beginning, we got you to import up to 2020 the data file. That's because this is true of up until the year 2020. The later years, 21 through 23, we'll deal with in a little bit. But there's a very good reason why we've split that, and yeah, that will all be revealed with time to come. So that was the lightning round of foundations. What is semantic reasoning and the basic queries? Yeah, we've got a question over here.
Yeah, for the object, subject, and predicates, like how are you assessing the namings of the existing database?
So how are we? Sorry, let me make sure I've understood this. Is this about this? That's right. So they're all part of our data. So if we go back to this like graph exploration of our data, which it was on one of the earlier slides. There's a link to this. I think it's maybe slide 14, give or take. this is the data that exists in our data store. So we have imported this, we have made, or actually Ergast made these choices that we have now adopted. So now if we want to access any of these things, so for example, we want to access a driver's first name, we have to use the predicate driver underscore full name. And same for all the others. But yeah.
I'm a wired to RTF.
Okay.
If you would now have more people than Lewis,
Mhm.
how would it look like in this plot? Because
Yeah.
you show only one person here, right?
Fair question. Let's have a look at another person. So here is another driver called Vettel, and we can. So this is just a tiny little slice, and so there are about 200 drivers in total. I don't want to show all of them because it would be a mess, but yeah, this is sort of how your graph actually is, right? But no, great question. No, it's not at all, honestly. Any other questions? So that's the kind of the fundamentals done. Hopefully we all sort of share at least this basic level of understanding now that's going to enable us to do some reasoning.
So the green one is the class, right?
Mm-hmm.
And the driver Vettel is subclass? Or it's
So this is an instance.
instance. Okay.
Yeah. So, sorry, I should have explained that. The purple nodes here are instances of classes. The green nodes are classes.
Okay.
All the other stuff is like properties. So it could be, these are strings, whatever. Cool. So, on to a little bit of OWL. As promised, we have 4 axioms to cover. The first 2 are concerned with properties, the second 2 with classes, and yeah, this is where we're going to start adding new data to the data store. So everything we've done so far is just querying for existing data. Now we're going to start adding stuff based off these axioms. This is where it starts to get a little bit more complicated. So again, if anybody has any questions, please ask. I am going to also go through them quite quickly. So I really anticipate confusion and people not knowing what's going on, but it's quite difficult to judge in advance what your level is. So please jump in with questions, and I can kind of tailor this to you. Yeah, well, that's the hope. Again, we're going to start with some very basics. What is OWL? Well, OWL is an axiom used to write axioms and ontologies. And, well, what are those things? Well, ultimately, axioms are just assertions of truth. So they are just true statements that RDFox uses to make some inferences. So, like data might have been Lewis Hamilton has the first name Lewis. That's a fact. That's a very specific fact. An axiom might be all drivers are people, which is still a fact, but it's much more general. And RDFox will then take that and say, oh, this thing is a driver, therefore it's also a person. Pretty simple. Ontologies are just collections of axioms. There are lots of definitions, and other people here will give you other ones. They will probably be right as well, but at their core, it's that simple. It is just a collection of axioms, so even though it's this sort of scary term, you don't really need to be that scared of it. OWL is the standard way that ontologies and axioms are described. Easy peasy. We'll be using a syntax called turtle, but there are other syntaxes available. For anyone who knows what that is, you know. For anyone who doesn't, don't worry about it. And why do we need this? So we've already shown a little bit about what reasoning can do in general, but OWL specifically helps us out with a few things. And this family of drivers helps us show why it's necessary. So these guys are all from the Fittipaldi family. There's 4 of them. They were all Formula 1 drivers at different times. That's why they're in our data set. And we have this blank node here, who is Pietro's mother. She was not a Formula 1 driver, so she's not in our data set. She's just a blank node. But you can see that this is a bit of a mess. And if we look at what kind of queries we'd write, we can see why this causes some problems. If we look at Emerson and Wilson at the top, these guys are brothers. But the data that we have about them is that Wilson has sibling Emerson. So if we write a query that says, who is Emerson's siblings, or RDFox will say, Emerson has no siblings, because that's not what the data says. Likewise, if we say, who is Wilson's brother, RDFox will say, Wilson has no brothers, even though we read this and we know that these are true. This is a huge problem, especially if you're combining several data sets. Perhaps, we've got a has-child relationship here between Wilson and this other Fittipaldi. Maybe one data set talks about children, the other talks about parents. And now you're combining the two, and you have 2 ways to talk about the same thing, but no real way to deal with it. So either you have to write a query that accounts for all possibilities, which you're probably not going to do, because that would be a pain to maintain, and you're likely to make mistakes. Or you go through a pretty lengthy and difficult transformation step where you kind of do your very best to account for all of these things and to either change one to the other or import others or whatever. That does work, but it is hard, it is costly, and it's pretty rigid. So if you make a mistake, often you have to start again. If you introduce new data, you obviously have to do the whole transformation all over again. But we can just not do any of that if we choose to use OWL reasoning. And we'll see in a moment that we can infer like inverse relationships, for example. So every time we see has child, we can add has parent in the other direction. And it is as simple as adding in an axiom. And now every time we add in a new has child, additionally, this has parent will be inferred. So straight away, we can just query for has parent, even though our explicit data said nothing about that. That way of managing is very, very easy and is sort of one command rather than like anything else. And you can keep track of what you've inferred. So again, if you make a mistake, very easily take it all out, make adjustments, add it back. And again, we'll see this in a second. Yeah?
I have a question, but if you don't have a data for the parent, you have a Benjamin bond practically, right? So you have just an edge, but no node.
So you can't just import an edge,
Exactly.
as far as I'm aware, but you can. Sorry, let me make sure I've understood your question. Can you rephrase that?
I mean, you said that if you add has child, you can always add has parent. Okay.
Sorry, yes, I understand where the confusion is coming from. What I should have said is if you add a triple that includes this has child relationship, then a new triple will be added with the same 2 nodes.
But our way around.
Exactly. Yeah?
Quick question. Can you confirm
Yeah.
that if you have multiple triples like has sibling and has child,
Mm-hmm.
then it will add a has uncle or aunt or nephew or niece or whatever, like that you can do it through multiple relationships?
You certainly can.
Right,
Yeah.
thought so.
I won't be showing that,
No, fine.
but this is actually an abridged version of a different workshop that I sometimes give that's 4 hours. It's included in that one. So if you fancy that, come along later. But yeah, very good question. And in case anybody didn't hear that, we can sort of chain these axioms or make them as complicated as we want them to. So we could, for example, add has uncle being a father who has a brother, or parent who has a brother.
Do you do it with LLM or you give rules?
So, excellent segue. Oh no, almost an excellent segue. The first thing I'm going to say before we get onto these axioms is Protege is a tool that you can use to write axioms. It takes care of a lot of this for you. It's free and open source, so we would always point people here if you're going to do this. However, there's a sort of caveat to all of this, is you don't need an ontology. I can't stress that enough. We say this all the time because it has happened so many times where people have come to us, they have this beautiful ontology and they say, now I want to like do something with it. It's like, great, you're keen, this is awesome. And then they actually start writing queries and they actually start like importing data and they realize that their whole ontology that they spent months on isn't supporting the queries that they want to run and like isn't supporting the data that they really have. And when it's something that you don't actually need, that's like a huge waste of time and it's very frustrating and it sets back the project. And there's a good reason why people do this. It's because in SQL you need a schema, and so people who have traditionally come from there or have like picked up habits from that background, they come and they rush to an ontology, but that's not the case with graph. You don't need any of that. You can just start with data, start with queries, and then when you hit a roadblock, like you're combining data sets that need some transformation, that's when you head to your ontology editor, that's when you start supporting the queries that you want to write. Cool. So, now coming to your question, how do we actually make these inferences? With axioms. So this is the first axiom set, and as promised, it's around properties. In this case, it is has father is a subproperty of parent. So this is an axiom. We will come to rules in a little bit, but I want to rules are way better. But we'll we kind of need to set the sort of historical foundations because everybody uses OWL and has done for a long time. So in this case, we're saying that has father and has mother are both subproperty of has parent. Hopefully you can see that I've highlighted the like key parts of this axiom because the syntax of OWL is quite confusing, or at least I find that there's some stuff there that can mislead you. So if that's the case, just focus on the colored boxes. But on the right, you can see what's actually happened in our data store. So we have again, Emerson and Pietro and this woman in between. And you can see that our explicit data is Pietro has mother, his mother, and the mother has father, Emerson. And that's in sort of grayed out gray. In the blue is what we've inferred. So you can see that with our axioms, it has found has parent, and then between the two same nodes in the same direction, RDFox has inferred this has parent relationship. And it has happened for both has father and has mother. So now we have two has parent relationships between our nodes. So if we're writing a query, now we can query for has parent instead of saying show me all the fathers and show me all the mothers. Hopefully that's fairly straightforward. Does anybody have any questions about this or OWL in general? Yeah?
So, OWL is open world assumption? And Datalog is?
I think it depends on which shard you use. RDFox is closed world assumption. And so what this means, open and closed world assumptions effectively means if something is missing, do you assume it's missing or wrong? And closed world means if something is missing, we assume it's incorrect. And we'll come on to a feature that relies on that heavily later, and this is why we've gone down this path. But it's a really important part of all of this that actually a lot of people miss. So fantastic question.
Datalog is closed world? Or
Yeah, closed world. So all of what we do is closed world. And so one of the benefits of that is everything in your data store is guaranteed to be consistent and accurate with the rules and the data that you have. So if you have a legal database, say, and you do some inference, you need to know that the things that have been inferred are correct. And with the closed world assumption, you can sort of take that guarantee because it's not going to say, well, this was missing, so maybe it's true, maybe it's not. Does that answer your question?
Well, if you benefit from open world, you can
Yeah.
use that.
That's true. Yeah. So it's not. This very much is not a one's better or one's worse. It's depending on your use case. We find in practice that the kind of guaranteed truth is more important. But yeah, if the thing that you're working on specifically needs the open world assumption, then yeah, I'm afraid this is not gonna do you any favors. But yeah. Right. Two more things I want to say about this axiom set. One is this is not data validation, so this will not stop you doing anything. This will just add new data to the data store. So these blue facts have really been added to your store. This is not going to sort of restrict by any means that sort of father has to be a subproperty of parent. If you try and do something weird, this will let you. There are tools that will stop you. They are called shackle or again Datalog. So if you want to do data validation or some kind of constraint violation stuff, that is very much possible and is hugely important in enterprise, but we're not going to cover it. So if you want to talk about that again, stick around at the end, we can have a chat. But it's very important to remember that this just adds data, it's not sort of stopping you. The second thing that I really want to point out here is because, I mean, this kind of gives it away, but in these axioms, the inferred information is trackable. So RDFox keeps track of exactly what has been inferred and exactly what is explicit. And that's why managing this is so much easier. Because to get this picture, I've just run one command that is import this axiom set. If I find I've made a mistake, I just unimport the axiom set. These previously inferred relationships are removed, and I'm back to my base state. So I don't have to worry about really trying to keep track of stuff like I would if I just do a simple insert statement where I have to remember, oh yeah, last week I inserted this has parent thing, that wasn't already in my data, maybe I made a mistake, and now I have to go through and find all of this stuff that I have to now remove. Yeah?
How do you test that the axioms that you put in are sort of correct? Because you said you have to remove them. Is there a way of sort of running the same queries without those axioms and then with them, or do you have to actually remove them from the database? Testing is a question.
So that is a fantastic question. Yes, there are a few good ways to do this. The one I would point you to is a feature called delta queries, which effectively runs the same query twice, once before import, once after import, and shows you the delta. And they're great because they are super efficient. So it is just, I mean, it's a little bit more than the delta, but it's like a very small computation. Yeah?
Nobody will be talking about it, but I'm a Gen AI engineer, and my question is that I'm a lazy programmer. I don't know how you do it, but are there any Gen AI tools that can extract axioms from texts?
No, not that I know of. Yeah, I'm sorry. As a Gen AI engineer, that's probably not what we want to hear. But the sort of I don't know how to phrase this, but the real power in these axioms, in these rules, is that they are encoded expert knowledge or domain knowledge. So, all right, has father being a subproperty of has parent, pretty easy, right?
You could have a help tool for the domain, for the SVE, right?
You could.
To give it, just to correct it and validate it, that's it.
You could, but some of our clients, a lot of our clients, use these to do very complicated stuff. So you're using several layers of rules that are all doing very, very specific things. And the reason why they use it is because, and they don't use, or separately use like Gen AI, is because the answers you get are guaranteed to be accurate. So according to your rule set and according to your data, the results are true with 100% accuracy. And the second you introduce, LLMs or whatever, and that's really important, but at a different step, it introduces this sort of shadiness where, I don't know, say you drop to 99%, which frankly would be impressive, but going down from 100 to 99 is a huge step, right? Where, 99 to 98, not so bad.
That's what you do.
It does depend what you do, but a lot of where people would introduce LLMs is sort of at a later stage where you're like accessing the data. So you're accessing sort of a foundationally guaranteed correct source that you then access via LLM, or do then something with that data that's like Gen AI. But yeah, typically, or not typically, we would always encourage an expert to write this. But if you don't want to, there's nothing stopping you. So, you could ask ChatGPT to write you an OWL axiom and it would.
One thing, it's about time savings, efficiency, it's all about money.
Go for it. Yeah. I mean, really go for it. Like, if the trade-off for you is worth it, so that like you don't need that accuracy, and there are use cases where you don't.
Yeah, okay.
Stick it in. Like, there's nothing stopping you. Hey?
A gap in the market.
Yeah, maybe. But yeah, we would very much encourage people to yeah. Cool. Sorry, I thought I was way behind, but I'm actually on time. So no, please. Honestly, like the questions are fantastic.
I had a question about the multiple axioms referring to the same properties.
Yep.
If you have many axioms that are applied sequentially and then you want to go about removing them, and if, say, 3 axioms add the same property, is that being tracked? And can you then query for a given property which axioms, or is it handled in a graceful way?
So that's a fantastic question. You've jumped ahead of me. I was going to talk about this with the next axiom set, but I'll get to it now. The question was, effectively, how do we manage duplicates? So, what if has parent is inferred in 2 different ways by 2 different axioms, and how do you deal with procedure? So if I have an axiom that relies on another axiom, is there a scenario in which the sort of second one can be inferred first, and then the first one, meaning that I don't end up with this full set? Is that right?
Yeah, well, like conflicting ones, overriding, like
Yeah.
any kind of mishmash of that.
So the short answer is you don't have to worry about it. The long answer is if there are several axioms that infer the same property, RDFox will infer that singular triple once and recognize that there are 3 sort of supporting pillars. Obviously, we've been talking about removing them, so if you then remove one of those pillars, the other 2 still hold. So this fact remains. So it's not as though like this one is inferring this, it's that it is inferred by all 3, and as long as one remains, the fact remains. As far as procedure goes, it's the same deal. RDFox will figure out which order they need to go in, and that is particularly important if they're sort of self-referential or cyclic. That's another question we get all the time. What if sort of something infers something that infers something, and then you're back around to the beginning one? It will infer the cycle and then stop. And this is sort of calculated in a very clever way that means the entire set is always inferred. So it will keep trying until no more is being added. So yeah, no worries there. But yeah, another fantastic question. Any more? Yeah?
Real world question.
Yeah.
Out of all your customers,
Yeah.
how many of them use these OWL axioms and how many do not? Roughly.
I mean,
Everybody?
almost everyone. The sort of truth of the situation is most people use both Datalog and OWL. So most people have an ontology that they like and they use, and then use Datalog rules to do like aggregates or negation or these like filters or whatever, you know, the more like business oriented reasoning, but the ontology still stands. And sometimes it's just useful. Sometimes it's a legacy thing, but it's yeah.
Are you going to talk about when to use Datalog versus when to use OWL?
Yeah. So, as a sort of an intro to that, ontological reasoning, probably the easiest way is to do it with OWL if it's a big ontology, and if you're sort of mapping that out and you have an ontologist, which is kind of how a lot of people approach this in practice. They might build it up in something like Protégé, which handles some of that for you. Great. Stick it in, you're done. You could do that in Datalog if you want, and who knows, maybe we'll get to a point where actually more people are trained with Datalog and that becomes easier and quicker and all the rest of it, in which case there may be a shift. Like, you know, that there's no reason why that wouldn't happen. But then there's a load of stuff that OWL can't do. And whenever you run into that, which it is frequently, that's when you turn to Datalog. Yeah?
How many, in average, how many axioms does one graph usually have?
I mean, how long is a piece of string? Like, how many do you need? You know, if you need one. If you need a million, use a million. It won't be, but you know, it is entirely dependent on the use case. But yeah, I think
Not that much also. So the question is, the
Yeah.
answer is not that much usually, right?
yeah, I think in our for the F1 demo that I don't know if anybody actually did click on that, but anyone who did, I think we have about 300 or 400. So yeah. So you know, a fair number, but those weren't written by hand. So we didn't sit and write these out. We used Protégé, which is an efficiency tool, and is much better. So yeah, cool. So I don't know if that gives you an estimate, but it's like it really is. Like if you don't need an ontology, use none. You know, don't use any at all. So yeah. Cool. Right, axiom set 2, inverse properties. So this is similar to the last axiom set, except now we are inferring a relationship in the opposite direction to one that already exists. So in this case, we are looking at result driver and driver result. So our explicit data in grey is this result has a result driver, this driver. With this axiom that just says result driver is an inverse of driver result, we are inferring in the opposite direction between the same two nodes, driver result. Pretty self-explanatory. This is the sort of thing where we're looking at parent and child that's really, really useful. And part of the reason why that is so useful is bringing this right back to the start. These are just statements of truth. So there is no directionality to these axioms. Result driver is an inverse of driver result, means driver result is an inverse of result driver. So in this case, our result driver was our explicit data, so driver result was inferred, but it could very easily have been the other way around, where driver result was our explicit data and result driver was inferred. And that's really important when you're combining two data sets. You don't want to have to write two axioms that just do the same thing in different directions.
So if you have an H result driver, could add another H.
Yeah, perfect. And again, this is great. You don't have to worry about cycles. You don't have to worry about duplicates. You don't have to do any of that because of the procedure discussion before.
Is there ever a concern about all these axioms adding loads and loads of triples? Is there a philosophy of what to pre-compute via these axioms versus like writing complicated SPARQL queries like you did at the very beginning?
Yeah, totally. And again, that depends on your need. So it's unusual. I don't think we've ever come into a situation where people weren't able to like sort of buy a machine big enough to house their data. In this day and age, you can buy like obscene machines for next to nothing on AWS. So it's not a sort of hard limit, but of course it does cost money. So you do want to be conservative about what you do and not just add stuff because you can. That being said, the overhead of these triples is not massive. So I think, again, it entirely depends on your axioms and your data and all the rest of it. But we say between 60 and 100 bytes per triple. So you're not adding vast amounts. But don't be silly with it. It won't this kind of thing won't get you into an infinite loop of this won't infinitely insert queries. Infinitely insert relationships. You can write rules. I'm not sure if you do it with axioms, but you can write rules that will run infinitely. But there are kind of warnings along the way. So if you do that, it's because you've made a mistake, effectively, or done it intentionally, but with the sort of intention that it will run forever because you want to stress the system. There's one more thing I was going to say on that. Oh yeah, that's the one. So it depends really on how quick you want your final system to be. So we have some use cases where they need answers instantly, or as near to real time as possible. In that case, memory is not a problem. They buy a huge machine, add all the data, and then just run a query that is near instance. If it doesn't matter, maybe you're not running a sort of client-facing system, then be much conservative, write more complex queries, have it take a little bit longer. It really is in your hands to decide that trade-off, but it is unfortunately a sort of inherent trade-off of these systems.
Why don't you vectorize it and do a vector search, which would be much faster?
So you can do a vector search if you want, but they're just sort of again, it's sort of pros and cons. So we have a RAG demo that uses a vector database to vectorize some of the data, but you lose the reasoning piece because you can't do reasoning over a vector database. So you can combine the two, and that's what we do in the RAG demo. Again, there are sort of trade-offs by introducing a new technology. You have to connect them. There's another point of failure, another point of maintenance, that sort of thing. So it's at this point we sort of get into the weighing of architecture, which is way beyond what I am qualified to talk about. Okay. But effectively, it's your choice.
How's it called, the feature?
This one, reasoning?
Vectors.
Like vector search.
In your technology.
So we don't offer a vector search. So nothing in RDFox is a vector database, but you can connect to one and do it that way. So.
I know it's not that really possible.
Yeah.
Exist.
Yeah. Sorry, but we've done some stuff with ChromaDB. I think is a vector database. Yeah, getting thumbs up. So yeah, so it is possible if you want to do that. Yeah. Cool. Any other questions? This is great. This is there's loads. Yeah.
You're going to talk about performance, what axioms would kill performance?
What axioms would kill performance?
You can have as many as you want to run, but
yeah.
It does cost, right?
There's an upfront cost. So at the point that you import the axiom, there is a materialization stage where all the facts that will be inferred by that axiom get added to the store. So if you're writing an axiom that adds 1 million facts, that's going to take 1 million facts worth of computation. After that, you're just running queries. So it is there's no additional computation overhead. It's just the query.
Because it already ran the reasoning.
Yeah.
But that stays in the memory, right?
Yep, so it stays in memory. So yeah, RDFox is an in-memory store, which again, 20 years ago would have been a massive problem, and that's why we didn't have any clients 20 years ago. But these days, you can buy a terabyte of RAM on AWS and store whatever you want, and it's lightning quick. So, do you have a follow-up question, or was that? No. Yeah, fantastic.
So again, the comparison between OWL and running Datalog, which is by the way Swirl, that is a subset of Datalog.
So not quite actually. Swirl is sort of like an so Swirl is another rule language for those who don't know, and it's kind of like an in-between point. So it's a little bit more expressive than OWL, but doesn't really do a lot of the stuff that we want it to. So it's almost there, but then Datalog goes like another leap further and allows you to do loads more again. So we do support Swirl, and what actually happens within RDFox itself, whenever you import axioms or import Swirl, they get translated into Datalog and then imported, because Datalog is sort of a coverall that then does these other things too. So
the performance of running a reasoner on OWL compared to Datalog would run also much faster?
If you're running reasoning, it would be the same, because on import, you get an OWL axiom. It's just literally translated to Datalog, then the Datalog's imported. So actually, it's literally running the Datalog. So they would be the same. Cool, thanks. Right, last two axioms. I'm going to breeze through because I'm a little bit tight on time, and I want to get to the Datalog because that seems to be where a lot of the questions are anyway. So these last two axioms are about classes. So we've looked at relationships, now classes. In this case, we're going to use a union, which is where you get to say one thing or another, and we're going to say the class of a podium is equal or is an equivalent class to anything that is or that has a result position order 1, 2, or 3. So in Formula 1, for those who don't know, it's said that you finished on the podium if you finished first, second, or third. So we are literally just saying, if my result has position order 1, 2, or 3, then it is equivalent to being the class of a podium. I'm not going to go through the syntax because it's complicated. I don't have time. But if anybody wants to talk about it, come. Yeah, it's in the PDF. Yeah. Likewise, axiom set 4 is similar, but this time we're looking at class intersections. So this is where we say one thing and another. In Formula 1, before race day, they have a kind of fastest lap competition, and whoever finishes the day with the fastest lap is said to have finished on pole, and that means on race day they get to start first. So actually being like having won a race and being a pole sitter, both are pretty important things, and like they're very desirable. So to be a race winner and pole sitter is a really cool thing. So we're now making this superclass almost that is race winner and pole sitter, where if a driver is both a race winner and pole sitter, it is then inferred that they are also a race winner and pole sitter. Again, giving you this other way to query directly for what used to be two things. Any questions on the classes? I know that was like a 30-second thing, so good luck.
So you have like classes, subclasses, superclasses, and same classes or equal classes?
Yes.
Equivalent classes, sorry.
So yeah, so you can do any of that within OWL, basically, and again, Protégé will help you manage that, where you've got sort of this is above this, and so on. So, yeah, no, fair question. But that's where OWL stops. So you just get this taxonomical reasoning where you can infer stuff about equivalent classes, or you can infer stuff about properties, but you can't go a little bit further, which is what we'll talk about in a second. But we need to import these axioms, see what happens, and then sort of talk about why this all happens. Anyone who is following along, I would recommend you don't do this because I'm going to undo it in a second, because the Datalog's going to sort of cover all of this for us. But it's important that I show you how and what happens. So I'm going to run two commands here. The first is to import the axioms in axioms.ttl to the name graph myAxioms. RDFox does support name graphs. We're not going to talk about it. If you want to talk about it, come at the end. This is because, again, axioms are just data. So we're just importing data to a graph. We then have to tell RDFox that the data we've just imported is actually an axiom, and that we want you to do something with it, and we want you to infer all the results of those axioms into our graph. So the second command, import axioms, just tells RDFox that the things in the myAxioms named graphs are in fact axioms. So let's.
Why is that necessary? I mean,
Um,
added to as triple, so should they know that they're axioms? What else are they going to be?
Good question. Pass. I don't know. Valeria, do you have an answer to that one?
You need to reparse that.
Yeah. Why import them as data and then import them as axioms? Why not just in one step?
Because when you import them as data, it's ambiguous what graph you want to apply them to. That's literally what it is.
Okay.
But you can import them directly in functional style,
Okay.
and then
Can you apply them to certain name graphs, not others?
Yeah.
Okay.
Cool. Great question.
That's a good reason.
There you go.
There you go.
So before I import my axioms, I'm going to prove that I'm not cheating by running the info command. You can see on these lines here, might be a little bit small, but we have 4.5 million facts and 4.5 million explicit facts. So we haven't done any reasoning. All of our data is explicit. These are the 4.5 million that we imported right at the beginning. Now I'm going to run import axioms and import axioms myAxioms. And I'm going to run info again. And voila.
There's an open library for the axioms, I think, for each domain somewhere, right? So
They're
that's
yeah.
used a lot. I know that.
I would think so.
Yeah.
For some like common domains, there'll be
Yeah.
like ontologies and stuff readily available.
Colleagues were once giving me that. Yeah. So
Yeah.
in principle means that you can write your own, and then you can also download from
Yeah.
somewhere else, right? And
Yeah. So you can steal other people's ontologies, and that can be a huge time saver. It
yeah.
also means that you may end up with stuff in there that you don't want, and it may be lacking stuff that you do want. So you have to be a little bit careful about it. But yeah, I mean, a great place to start if you can find one that's roughly what you want.
Only that you need to validate it correctly, because if it's an open source, then it can be crap, right?
Yeah. So
Are there any standards for this? Like
Yes.
organizations who kind of,
but
you know,
not that I know, I'm afraid,
No,
off the top of my head. But if it's something that you're particularly like interested in, let's catch up afterwards, and we can like try and find you something that works. So I've imported my axioms in two commands. So I lied when I said one, but we now have 5.8 million total facts. So that means we have materialized 1.3 million facts, as simple as that. The kind of cool part is where I take these out again. So if I run import axioms minus and run info again, we're back down to 4.5 million. So I've made a mistake, I've undone it all, I'm back to my starting point. I can now reassess my axioms. So it is as simple as a single command to manage these axioms, which is just impossible with things like import queries. So for cleanliness, I'm also going to clean my axioms graph. So there is nothing in my system that is axioms anymore. But it's worth talking about the limitations of OWL, because there are some limitations. There is a reason that there is more to the workshop. OWL, it is and was fantastic, but it doesn't go nearly far enough for most enterprise use cases, because taxonomical reasoning is a great place to start, but there are so many complications of the real world that cannot be represented by taxonomy. So functionally, we need to go a little bit further. There are also a couple of general limitations. One is that it doesn't support existentials, which ties into this open-closed world assumption. So if we look at our podium, which meant being first, second, or third, this will not be inferred in both directions, because how could it be? If a result is second, that's fine. We know it's podium. But if our explicit data has nothing about the position order, it just shows that this result is a podium, we don't know whether it was first, second, or third. So we cannot infer anything. And actually, I breezed past it, but we got a handful of errors here when I imported those axioms. This is what these errors say. It is, you have some axioms in here that cannot be inferred in both directions. I will not deal with existentials. What I will do is infer it in one direction, but I'm just telling you these are exceptions. So everything else goes in both directions. These ones here go in one. Generally speaking, you'll know that already when you write the axioms, but it's important still that you are aware if you happen to get an error like this, a warning like this, not an error because it will still keep going. It's not a problem, but if you expected it to do something, yeah.
What's the limitation there? Because that's logical.
Yeah, so it's kind of like,
it's just you don't like
it's,
the warnings.
Yeah, if people see a warning, they're like, oh, like what have I done? And it's like, actually, it's done what you wanted it to do.
Yeah,
but
it's as you've directed it, so you don't want this.
Exactly.
This warning back. Okay.
Exactly.
That makes sense.
Yeah. Any other questions?
I just have a question. If you're talking about inferring things
Mhm.
in the reverse way. So,
Mhm.
for instance, if you know that somebody else was on the pole,
Yep.
was in first, and someone
Yeah.
else was in third, okay.
They must
and
be
then
second.
They must be second. And
Yep.
You can do that in Datalog.
You can do that in Datalog.
You can't do that now.
You can't do that now.
Exactly. That's.
Nailed it.
Are you going that way?
Yes.
Okay, fine.
No. I'm not going that way.
I'm gonna leave now.
But that actually,
That's what I wanted to know.
we should add that to the workshop because that's a great example. So you could do that with Datalog. So for those who didn't catch that, basically if you have additional information that narrows down the result. So we have, in this case, we have a result that we don't know the position of. In the same race, we have somebody who's come first and third. We would read that and know that they must have come second. You can write a rule, a Datalog rule, that would capture that information and add it in. Again, it relies on you having enough additional information to fill that gap, but as long as you do have the supporting information, absolutely fine. Cool. So kind of in the similar vein, this axiom here, where we combine pole sitter and race winner, this is just, he is a pole sitter of any race and a race winner of any race. That's where he gets race winner and pole sitter. But if we want from the same race to be a pole sitter and a race winner, can't do it. It seems like a really simple axiom, but you just can't do it in OWL. However, in Datalog, that kind of thing, same with the first, second, third thing, that becomes trivial. So, we've done all the OWL reasoning stuff. Any questions about OWL? We had quite a few, so I'm hoping we caught them as we went, but that's great. Fantastic.
Oh, can I just ask?
Yeah.
I guess it's
Yeah.
more like philosophy, but
Cool.
so you said OWL was really widely used, what everyone uses.
Yep.
But then you also said that it's not powerful enough to cover most enterprise use cases.
Yep.
So what are they using it for?
Very good question. Enterprise use cases is the truth.
Right.
But it comes with these downsides where people typically come to us when they have a speed problem, and that's why our jumping in point is always speed. So Datalog does stuff that is sort of functionally more advanced than sort of queries or anything like that can offer you, but nobody knows about that, so you can't be like, oh, it does all this other cool stuff, because like, I don't care. What people do care about is, I've got a system with an ontology, but it's powering my website and it takes my users 10 seconds to find what they're looking for, and I know from my web stats that 50% of people close the tab after 6 seconds. How can I get it down? We then say, here you go.
Speed's the entry point for you.
Speed's the entry point.
But there's a lot more power in Datalog.
Absolutely.
It's about having declarative logic. Whereas
Yeah.
in most organisations, you could model the business, but the complex declarative logic would end up being the logic would end up being in code.
That's right.
The code becomes more complicated, and the code gets copied everywhere, etc.
Yeah.
So this is really what it's about. It's about moving that to the declarative logic.
Yeah, absolutely right. So, in case people at the back didn't catch that, in existing enterprise systems, a lot of the time you'd query first sort of all the data you need, and then perform some like Python or whatever on top of that to actually do the analysis, and then serve it up to your user. But you're creating and having to maintain a code base that is sort of a high skill thing. It's also like difficult and costly, so you don't really want to do that. Instead of doing that, you can just have a handful of rules that are like much easier to maintain, to work with. Probably at the minute it's harder to find the skills, but within this room it's probably not harder to find those skills. So if anyone's job hunting, talk to each other. Cool. So that's OWL out the way. Now on to Datalog. So in Datalog we write rules, and they look a little bit like this. I'll show you a real example in a second because this is a little bit abstract, but basically the rule is split broadly into 3 sections. You have the inference symbol in the middle. Everything before the inference symbol is called the head. Everything after is called the body. And you can read this like a Sparkle query, so it's intentionally designed to be like a Sparkle query, as A is true whenever B is true. So B, the body here, this is your graph pattern. Wherever you find this graph pattern, A is inferred and added to the graph.
Datalog is a tool, right?
Yes, it's a language. So,
It's a language.
yeah. So here is an actual Datalog rule. So maybe this clarifies that a little bit. We have a graph, or we have the inference symbol in the top right. Everything after that is the body. And we have this graph pattern that connects the result to the race, the result to the driver, and then in the head is what we infer. So wherever we find this pattern, which is a pattern that we relied on in the count, in the Sparkle query a lot, we infer a direct connection between the driver and the race, has raced in. So this has raced in property is a new property that we are adding to our graph.
Why you do it only for properties?
No, you can do whatever you like. So in this case, we have variables with the question marks and data in the red. In this case, all of them are properties. We'll see examples in a little bit that aren't. But you could do like data in 3 positions. And actually, if you're being lazy, that's a way to just insert a fact. I wouldn't do that. It's bad habits. But you can if you want, and just have no body. So it's just wherever nothing is found, insert this thing, which, yeah, probably shouldn't have said that. Don't want you doing that. Please don't. But you can. I don't know if anyone's still following along.
Yes,
Yeah? Awesome. So,
2 hours long.
yeah. Awesome. I worry because it's so quick. I worry that nobody can actually keep up with this. But I'm going to import a rule and run a query that relies on this rule. So unfortunately, I am back to the terminal, so there's no nice UI for rules at this very moment in time. So we're going to look at rule 1 on the left and our query Q11 on the right. Right, is this? Let's make that a little bit bigger.
So you use them in combination, always, all in
Yeah.
Datalog, right?
Yes. So I mean, it really depends on your application. If the few demos that I've like hacked together, I would just use Datalog because
Only Datalog.
yeah, but that's
You do
because
this whole ontology just using Datalog.
so I then wouldn't use an ontology, but those are in relatively simple use cases. In practice,
Yeah.
normally you have some form of ontology because somebody's worked on it, or because you've found one online,
Okay.
or really because it is what you need, and
Yeah.
you know the thing you're modeling is an ontology,
Yeah.
and in that case, you need an ontology because you're modeling an ontology. And in those instances, yeah, you export that in OWL from Protégé and then import it to RDFox. But again, that'll be turned into Datalog, so it's kind of like everything leads to Datalog in the end. But yeah, in practice, I'd probably use both. So yeah, here's our rule. It infers this has raced in predicate between whatever driver it finds and whatever race it finds, given this pattern. We're then running this query that relies on this has raced in property. So we're querying for something that uses the property in our rule. Pretty easy. To run this query, we're going to use evaluate. What is it? Queries. Q11.rq. So I'm going to run it first, and we should get nothing because we haven't imported the rule yet.
That's an AND relation, or?
Yes. So the question was, is this an AND relationship? And so actually the answer is no, because what this is a graph pattern. So what you're describing is a pattern within a graph. But you're absolutely right to assume it's like an AND, because both of these have to be true in order to make the inference. If you need like an OR, you can have a couple of different rules with the different bodies, because they're effectively different rules at that point. So there goes query 11. No answers, as promised. There's no cheats. We're then going to import rule 1 and run the query again, and suddenly we have loads of data. Or loads of answers, I should say. So again, with one command, we've imported a rule. RDFox has imported all of these queries, all of this data, and now we have our drivers and what is it? Yeah, the races they've raced in. So just like that, we have this new property accessible. Any questions? Yeah.
So you put the equivalent sparkle on the what's the difference between
So good question.
logging it as a rule and sparkle?
So yeah, this Sparkle insert query effectively does the same thing, except I can't track. There's no difference between the driver has raced in race triple and all my other triples if I use an insert query. So what do you mean? Different name graph? Yeah, it could do. Then you have to then know that it's in a different graph. If you hand over that system, it may work slightly differently, but it doesn't. Oh, and also, these won't work with incremental or anything incremental. So if I then add new data, you then have to go through the same step. And again with retraction, so if we're retracting a driver or something in this context, doesn't really make sense, but say that it does, this would be a fixed data point, which it wouldn't if we're doing it in rules. So, but yeah, fantastic question. Yeah.
Can you say anything about Datalog versus Shackle? Because I can do some of these things in
Yep.
Shackle, but maybe not all of them.
So we also support Shackle for like data validation. Is that what we're thinking? Yeah.
Validation, yeah, exactly.
So you can also do validation with Datalog, where you effectively import like this is invalid, provided the conditions of something being invalid. So you know, a driver can't be a dog. So I put a driver is a dog. Import that it's invalid. So that works perfectly fine. Some people use Shackle if they want to use Shackle. If you use Datalog, if you're used to writing Datalog. I don't know. I haven't really used Shackle that much, to be honest. So I don't know the syntax, but maybe you can. I mean, certainly there's nothing you can do in Shackle that you can't do in Datalog. But I wonder if there's you can be sort of more expressive with your constraints. Because I mean, in Shackle, can you do like aggregates and negation and stuff like that? Yeah. Oh, well, then I'm not sure.
Shackle, they go into a different name graph.
Oh, do they?
Yeah.
Oh, yeah, that's right.
A graph for the rules.
Yeah.
A graph for the data.
So, yeah, that doesn't happen. You may or may not want that, but again, it's
just,
your choice.
There's a lot of choices.
There are lots of choices. So, this we say this a lot. Like this is a tool. It's a very powerful tool that we hand to you and now say, you know, we'll help you, but like this is up to you to make these choices. If you want to choose to do something insane, you can do something insane. It will probably warn you not to, and we will definitely warn you not to. But if you want to, by all means, go for it. Yeah. So you can write a construct query that sort of creates these new like properties effectively, but they're like immaterial, so they're not stored in the data, so it would be much slower. So anything you compute, you have to compute at query time. Whereas with this stuff, it's pre-materialized, so anything you query for, it's like it is the same compute as just a find and return query, whereas construct is going to be a lot slower, unless you're doing something super simple. Is that kind of getting an answer?
So it's just faster?
Yeah, and you know, easier to maintain, incremental, like all of these. It's basically the same benefits all the time. It's faster, easier to maintain, and you can do incremental reasoning where you can, you know, we're adding new data, new rules, retracting stuff on the fly, and it's maintaining itself up to date. If I wanted to do that in a construct, I'd just have to rewrite the query, which, you know, you can do, but you're just going to have to do it again and again and again and again and again. So, yeah. Cool, yeah?
I had a question about like just QC workflows. Like, is there a way to go from property to what led to its...
Sorry, what's a QC workflow?
Just like if you're wondering where property came from.
Mm-hmm. Oh, yeah.
You go backwards to figure out what.
Yes, you can. That's a great question. Oh man, I've only got 10 minutes left. Okay, I'm going to breeze through this next little bit, but this is a really cool part, so I want to show it off. So let's make a search for these things and explore the results. So we now have a bunch of drivers who are directly connected to a race. We can explain these inferred relationships in our explain tool. So here is the new relationship, and off screen, this is why it is there. So you can see this relationship was inferred because of this rule. This rule was triggered because of this data. And there is an exact proof of why your data looks like it does. And so if you are like, oh, well, that shouldn't be there, go back, use this tool, find the rule that you've written that's wrong, find the data that you've imported that's wrong, and then go from there. Sorry? Yeah. So we've gone from an imported fact to its origin, which again is pretty cool, particularly in this world of like LLMs and like black box stuff where like nobody knows what's going on. Okay. So we're very short on time. I really want to show you the coolest stuff, so I'm gonna skip through loads of stuff and just point out what's cool. So in this rule, these are also exercises. If you want to do these in your own time, please do. They're not very difficult, so give them a go, but it will get you used to like writing Datalog. But here you can see that we've used a filter in a rule. So we found a graph pattern. In this case, we're finding the result and then then finding the position order. So is it first or 10th or last? And then saying that the position order must be less than 4. And in this case, infer that this driver has a podium in this race. Quite cool. In this one, we're doing an aggregate. So we're saying count the number of races that this driver has raced in. And again, we're using this new has raced in relationship that we inferred with a previous rule. So these are rules depending on other rules. Count the number of races that they've been in. And now we're going to infer this new fact, driver has race count, race count. So again, this count is now a fixed, sorry, not a fixed, it is a fact in our database that has been inferred by a rule. So again, if they get a new race, it will automatically be updated. The count will increase incrementally without you having to do anything. Super easy. Rule 4 is exactly the same. It's about has race win count. Same aggregate, except now we're assuming or requiring that the position order is 1. And again, we're using like binds here, so you can perform complex calculations within the rules. So you can do things, in a second we'll do a win percentage. So again, just one thing divided by another. You can do, like, in one of our demos has something that's akin to like time frequency analysis. You can get pretty advanced with it. So all of this again is done within rules, so that at query time, you just query for the answer. So again, it's incredibly quick, almost sort of real-time answers. Anyway, sorry for the real rush. I really prefer to like focus on the questions because I think that's where the like main value comes in here. But this rule, I really want to focus on and spend a few minutes talking about because it's super important. So we've seen graph patterns, we've seen aggregation, we've seen filters. These are all things that go way beyond OWL and let you encode stuff like finishing first, second, or third, which is not that complex of a concept, right? But it could not possibly have been done with OWL, and now our like business logic is encoded in what is really quite a simple rule. This next thing is about negation, which is the absence of data. So here we are using our has podium in race property from the last rule and saying for any driver where this doesn't exist, infer that they are a driver that is a driver without podiums. So give them the class driver without podiums. And so if they have not got this property, it will be inferred that they're a driver without podiums. Now, this is a bit of a problem because we also offer incremental updates. So what happens if now, for example, a driver the next year wins a race and we add this data in? The reasoning engine has to keep track of these negatively inferred facts and remove it because now data has been added that invalidates the previously inferred triple. So we would have to retract a fact based off the addition of entirely separate information without ever specifying that we want to remove that fact, just because the rule already exists and this new data also exists. As it happens, in 2021, George Russell achieved his first win, having raced in F1 for a couple of years. He went from being a driver without podiums to a driver with podiums. So I'm going to show you the sort of results of that now, because again, it really is quite impressive how like easy this is. So I'm going to quickly run through and add my other rules. How far did we get? Rule 5. Okay, so there's all the rules imported up to the negation rule. So if we run our George Russell query, which is just Russell, we will see that up to the year 2020, which is the data that we've imported so far, he is a driver without podiums. So this query, this Russell query, just queries for everything that we know about George Russell. We can see why, because he's had loads of races, but we don't have anything up here about wins or podiums or anything like that. Just that he has raced in races and that he is a driver without podiums. Now, if I go ahead and import data, what's it called? 2021, oops, 2021, 23.ttl. Just like that, 500,000 facts imported again. Now if we rerun our George Russell query, we can see that he is not a driver without podiums anymore. This fact has disappeared. Or it has not disappeared, it has been retracted. And if we scroll all the way to the top, we can see he's got a lot more races, but also he now has loads of podiums and a win. So of course he's no longer a driver without podiums, but that fact has now been incrementally retracted, which is one of like the hardest problems that you can solve in like incremental reasoning. So this is why a lot of people don't do it, because that's really difficult. But it is in fact a solved problem. So rule 6 just shows you the calculation. So comparatively, that's boring. Does anybody have any questions about that? Because again, that was unbelievably quick. Yeah.
Question about another. If you have an
Yeah.
example of a query. So if you have a sequence of events, and you want to say, okay, if I have this kind of sequence event with a lot of rules, that actually means transaction between this and this. Like, you understand what I mean?
I think so. As in like.
So if you look at what happens when you in banking, I'm not from banking, when you transfer money from one account to another, what actually happens doesn't look like that, right? It looks like a lot of events, but you want to create at the end another edge, right?
Yeah, that's absolutely fine, and that's one of the things that I was sort of talking about or alluded to when I say you can go beyond queries, right? Because that would be a very difficult thing to do, or impossible even to do with a standard query. So what you can do is you can write a recursive rule that is like self-referential, but steps along your chain. In fact, we have a demo that does literally what you're describing, where it like steps along the chain until completion, and then says and makes a new node and links all these things to this new node and says, this is my like chain node. These are all the parts of the chain. This is its total value or time, whatever. It's like a summary, and you've done that by just encoding one clever rule that will iterate over itself until completion. It's quite advanced. I could show you afterwards if you're interested. But yeah, it's a really cool feature that I wish we had more time to talk about. Cool. Let me show you one other cool thing. Not this one. Not this one. This one. Here we go. I'm going to run, what was it, query? No, that's not right, sorry. Query 13 and query 2, I think. So query 2 was our initial count query, where we did the has number of race count, looking for that. We can see that it took 0.05 seconds. If we run query 13, 0.001. So on what is really a simple query, you have got a massive reduction in time that it took to evaluate, right? And this is just because we are performing, in this query, we're performing a count at query time. With this, because of the rule that we've written, the computation for the count has been performed way ahead of time, and we can just query directly for the result. So, yeah, what was that? What order of magnitude? 50 times quicker? 56 times quicker on a 10-line query? Like, that's crazy. Imagine this, but now with a real production query that's 100 lines, and you have a sort of stack of rules all building towards your goal. You can really achieve something quite special. Right. There's a bonus exercise. Do it at home. Right. We're out of time. I'm going to rapid fire these last 5 slides with like 10 seconds apiece. RDFox is an enterprise solution. It has other things such as persistence, access control, high availability, external sources like CSV, SQL, that sort of thing. You can deploy it on device or on personal machines or on large cloud instance. This is something that we didn't cover but is really important, so I'll come back to it. Oh, so's that. Shit. Okay. If anybody wants to go, I'm not going to stop you. I'm going to talk about 2 things that are really important. One is the types of reasoning that you can get. The other is how this fits into RAG. So one is sort of important for us. One is important as like the topic of the day. This one, the different types of reasoning. You have pre-materialization, which is what you've seen today, where you upload a rule or import a rule. Everything is materialized, so you pay the computation cost once, and then you can query for the result with, like, as a query for a piece of data. The other type is query rewriting, which is like, we hate it because it gives reasoning a really bad name, because what it does is it literally rewrites your query as you execute the query to incorporate these other things. So if you take the count example, it doesn't perform that count up front. You run the query, then it says, oh, you were supposed to do this count, so I'm going to do the count now. And then every time you run that query, you perform the count. And so it doesn't give you any performance benefits whatsoever, and it's really rubbish. So don't use that. Only go for people who are doing materialization. But then within that, often materialization is just OWL, so you miss out on negation, you miss out on filtering, binds, aggregation. There's no incremental, there's nothing like that. So you can't do all this other cool stuff. So again, if you are looking at reasoners anywhere, just make sure you're like asking these questions, because reasoning is a relatively new term. So a lot of people say, oh, you've got reasoning, great, you can do all of this stuff, but you can't because it's a broad term, but the industry hasn't really adopted the specifics yet. It's still just this broad church. Where does all of this fit into RAG? Well, effectively, today you have sort of 3 pillars that you can choose from. One is just using LLMs. It's really good. 10 years ago, this would have been magic. It's incredibly powerful. You can ask it whatever you want. Anyone can use it, but it has the slight downside of lying to you, which sucks. So, kind of actually a lot of people in our community came up with RAG, which is where you ground these answers in data, and you often use a vector database for it, which is fantastic because now you're getting truth out of your system. However, RAG restricts the questions that you can ask, so you lose some of this flexibility and power. You still keep a lot of it, which is why it's why it is so like such a hot topic at the minute, but it is much more limited. So if you want to do something like talk to a chatbot and just say, find me something that's approximately what I'm after, and then return it to me, great, stop here. This is all you need. It'll be fast. It'll be everything you want. But if you want to ask some of these more complex questions again, you need RAG and reasoning. And this is where people have started to talk about neurosymbolic AI. I've already heard that like quite a lot at the conference already. So I think that's probably going to be the new sort of buzzword in like 6 months or a year or something. But neurosymbolic, it enriches your data store with these with this data that gives you things like counts or like filters or like more complex business logic that you can now use RAG for and now get directly. So the perfect question that or the perfect question to ask each of these systems to sort of demonstrate their flaws and achievements is, how many things do I have? This will make up a number, this will not know, and this will just spit out the answer straight away. And all you're asking is count something. And like, you need that in business, right? Like it's enterprise does not function without things as simple as counts. That's, forgetting all the other stuff that we can do. If it doesn't pass that threshold, it's not good enough. If you want to see a demo of that, come see us or stick around. I would show it, but yeah, we're like way out of time. Congratulations. Thank you, everybody. Thank you for bearing with me. Well done.